my topic today is some of the methods we have especially developed for high-dimensional reliability problems. And one of the traits of these methods is we are using a so-called hyper-spherical formulation. And I will discuss what is the hyper-spherical formulation. And this talk should be given by Professor Junho Song, but he is now fully occupied in applying for some research center in Korea. So I'm doing this on behalf of him and also on behalf of myself. So yeah, the motivation is why we are so interested in the high-dimensional reliability problems. Is there any fundamental difference between the high and the low-dimensional problems? Well, perhaps there is no fundamental difference because the dimension can change gradually from low to high. However, there are some unique geometrical properties of high-dimensional Euclidean space and also the high-dimensional probability space. And one of the obvious observations of the high-dimensional Euclidean space is the volume explosion. Well, we can easily see this by considering a hypersphere inscribed within a hypercube. And if we divide it by the volume of this hypersphere, divide this volume of a hypersphere by the volume of the hypercube, as the dimension approaches to infinity, we have this ratio close to 0. So this is evidence of how large it is, the high-dimensional space. And also, we have the volume concentration in the high-dimensional space. We can see this by considering a uniform partition of the space. And if we take the volume in the central area divided by the volume outside, this ratio will exponentially goes to 0 if the dimension grows. So also, you can also see this trend by studying the volume of the hypersphere. And for in high-dimensional space, the volume will be concentrated more on the shell of the hypersphere rather than inside. So the conclusion is the volume tends to concentrate in the tails of the space. And for the high-dimensional probability space, there may exist a typical set. By a typical set, I mean the set which contributes the most to the probability. If we consider a generic event in this probability space, we can always write this probability of this event as the integration of the PDF over some region. And for a lot of conventional distribution models, we have the PDF decrease as the point is moving away from the mode. And also, we see from the previous slide, we have an exponentially increase of the volume around this mode. So as a result, there might be a typical set lies in between some very, very far region from the mode and also some very close region. So this typical set may contribute the most to the probability. And for high-dimensional standard normal space, this is the space where conventional structural reliability problem is defined in. So the typical set for this space is a hyperring. And well, this is because there is a trade-off between the exponentially decreasing probability densities with the distance from the mode, and also there is a exponentially increase with the spherical area with the distance from the mode. So as a consequence of this trade-off, almost all probability is distributed within this important hyperring. And well, you can see this for dimension like 400, and 95% of the total probability is contained here in the 20 plus and minus 1, the ring with the radius of 20 plus and minus 1. So because the previous speakers were talking about the design point. Here, in terms of the probability, the contribution to the probability, the design point may not be important because the volume around this design point integrated by this high density makes an insignificant contribution to the total probability. The total probability is located here. But the direction of this design point is still important because it points out the direction of the failure mode. By the way, so the important ring is introduced in our field by these two scholars in 2008. So this is the contents I will like to discuss today. So I will introduce this hyper-spherical formulation, and then two methods we have developed using this formulation. And I will conclude with some directions for future research and the summary. So this is the hyper-spherical formulation. It is a one-dimensional integration, and this R represents the sampling radius, and this theta R is the so-called failure ratio. It for a specified radius R, this failure ratio is the surface area inside this failure domain divided by the total surface area of the hypersphere with radius R. And this F sub chi is the PDF of chi distribution. Because this is in the standard normal space, so the random distance in the standard normal space follows the chi distribution. So here we have this one-dimensional integration to write the failure probability. And we can also project this failure ratio into this unit hypersphere. And also we can use a Monte Carlo simulation to estimate this integration. So this R sub I is the random distance drawn from the chi distribution. And this formulation is valid for any dimensions, because we do not introduce any approximations in developing this. This is just a correct formulation. However, it's especially convenient for high-dimensional problems. This is because the random distance drawn from the chi distribution is likely to be concentrated in this important ring region. And so the variation of this failure ratio with this radius will be expected to be small. So yeah, this is the hyper-spherical formulation, and I will use this formulation many times to develop different methods. Well, I'm sorry I don't have so many pictures, so you see the same one and also the same formulation. It will become kind of boring. Well, so the technique here is we establish an importance sampling density to estimate this so-called failure ratio. And well, this failure ratio can be written in terms of this integration. And this 1 divided by AN is the PDF of a uniform distribution on the unit hypersphere. Why uniform? Because in the standard normal space, if you fix a radius, then all point is uniformly distributed. So this I is the indicator function, which gives 1 if the point projected to the failure domain is in the failure domain, and it will give to 0 if it's otherwise. So we can introduce importance sampling density here. So we have this importance sampling formulation to estimate this failure ratio. And if we plug this into this formulation, we have finally the importance sampling formula for the hyperspherical importance sampling method. And here we have 2 layers. The first layer is to draw a random distance from the chi distribution. The second layer is to estimate the failure ratio for the fixed sampling radius. So here you see this Ri is drawn from the chi distribution, and this random sample is drawn from the importance sampling density. And from this formulation, you can see that the importance sampling density is built on the hypersphere. It's built on the unit hypersphere. So if we want to build some importance sampling method, we need a PDF model which is distributed on the unit hypersphere. And here the model we used is called the Wang Mises Fisher mixture model. And this is perhaps one of the most simple model on the hypersphere. And this model has a concentration parameter which controls how concentrate of the samples drawn from the model. And also it has a mean direction, which is the center direction here. And if we build a mixture model, we also have this alpha k, which is the weight for each component of the Wang Mises Fisher model. So by having this mixture model, we have the ability to estimate problems with multiple failure modes. Well, of course, how can we find the parameters of the Wang Mises Fisher mixture model? This is not a trivial problem. So here we are using a framework called cross-entropy based adaptive importance sampling. And I think Yasin has already introduced this perfect importance sampling density. Well, this importance density is perfect because the variance will be 0 if you can actually use this density. However, it involves the solution of the problem, which is the scaling factor, the failure probability here. So we cannot use it directly, but it is still helpful because we know the shape of the perfect importance sampling density. So this is the framework of adaptive importance sampling by minimizing the cross-entropy. The cross-entropy is a distance metric to measure the distance between two probability density functions. And we have the optimal importance sampling density should be the one which minimizes this distance from the perfect one. So if we consider this as an optimization problem, then this term is fixed, because although we do not know the perfect density, we know this integration is just a number. So what we do is to maximize this integration here. If we find the parameter which maximizes this integration, we will have the best model which approximates the perfect density. So, but how to estimate this integration is also not trivial. So the typical solution to this problem is to use a stage called pre-sampling to estimate to solve this optimization problem. And by using a small amount of pre-samples, we do the Monte Carlo simulation of this one and to solve this optimization problem. And Professor Song developed this cross-entropy based method by using the Gaussian mixture model. And so the importance sampling density is the Gaussian mixture. And there are two stages of the method. The first stage will be a pre-sampling stage. This stage, we find the optimal parameters for the Gaussian mixture model. And the second stage will be the final importance sampling. We use the optimized Gaussian mixture model to perform the final sampling. Well, one of the problem of this approach is it doesn't work for high-dimensional problems because of the reason because the reason is what I showed in the previous slides. In the high-dimensional space, you have a very narrow typical set. And if you use Gaussian mixture to estimate the typical set, you will have some singularity problems. So this is their approach to solve like low-dimensional reliability problems. And well, by implementing this framework, we have developed methods to estimate the parameters of the von Mises-Fisher mixture model. And this is quite straightforward. This is just in the machine learning field, what they do as to estimate the parameters of some PDF. And also, the framework will be similar to the Gaussian mixture one. We have the pre-sampling stage to get the near optimum parameters of the von Mises-Fisher mixture model. And we perform the final sampling on the hypersphere with radius drawn from the chi-distribution. And this is an example of two linear hypersphere parallel to each other. And there is an analytical solution to this problem. And here I show the updating process of the method. The horizontal line is the dimension, and this vertical line is the coordinate of the dimension. So for this problem, the design point direction is these two red lines. And after running this algorithm several times, we have the model approximate this important direction here. I think there's also a video. So this is how the algorithm update to find the importance direction. Okay, so this is another multi-degree of freedom system with some nonlinear constitutive models, and we excite this structure with I think it's white noise, and we compute the first passage probability of some certain story drift, and also we can use this method to compute the instantaneous failure probability, and also the first passage failure. Yeah, right now I'm going to show the extrapolation method developed using this formulation. So you see this picture again, and because I really do not have other fancy pictures. So you see this formulation again. This is the hyper-spherical. So the idea is very straightforward. So we build an extrapolation method by writing this failure ratio as some parametric model. So this factor V is the parameters of the model. And we estimate this one-dimensional integration by some numerical integration method. So why we can build an extrapolation method? This is because the failure ratio grows larger if the radius increases, given the safe domain is star-shaped with respect to the origin. This is the standard assumption for structural reliability problems. And if you see this picture, consider you increase the sampling radius to infinity. Then you can imagine the failure ratio approaches 0.5. So so if you increase the sampling radius, you have a very large failure ratio. And so the idea of the extrapolation is to find the parameters of this failure ratio given this estimated from very large radius. And then you estimate the failure probability using this numerical integration here. So the failure ratio model we used is a summation of hyper-spherical caps. So the hyper-spherical cap is just a region here. And if we consider the surface area of this cap divided by the surface area of the total hypersphere, we have a formulation like this. And this B function is a regularized incomplete beta factor. And here we have the parameter B, which indicates the distance from the origin to the center of the cap. And also we have the angle here. So the model we used for the failure ratio is a summation of the different hyperspherical caps. And we somehow write this alpha k by the distance from the origin to the center. Why we are using this? Because consider if the limit state surface is flat, then this distance will be constant with independent of the sampling radius. So we have the assumption that this B sub kr does not change dramatically with r. And if we assume this, we can assume the form of this distance as constant. If we assume it be constant, we will have the zero order hyperspherical extrapolation method. If we assume it to be a linear function, we have this first order extrapolation method. So the point here is this is a personal choice to select the model to estimate this failure ratio. And you can always consider other models, but we have found this model to be especially effective. So if we implement these two models of the distance, we have the failure probability can be estimated by this summation of the CDF. This is for the zero order method. And for the first order method, we can just solve this one-dimensional integration. We can use any typical numerical integration method to estimate this probability. So the procedures of this method will be very straightforward. First, we select a sequence of radius. And the radius should be large, so we can compute the failure ratio by using some, for example, the direct Monte Carlo simulation. And then we estimate parameters of this model. And here the error function, we are using this as the error function. And this weight here, we put more emphasis on more reliable data. So the final stage will be compute the failure probability using the formulation I showed in the previous slide. And also we applied this method to this simple series system problem, and we have found the performance of these two methods reasonably well. And also this is picture shows the change of this failure ratio versus the sampling radius. And here, the dot here is the data we used to estimate the model. And this is the typical set. So you can see the data here is very far away from the important region. But somehow, I think it's because the geometrical insight we used, it gives useful information. So even we have data here, we can estimate this region very accurately. And also we studied this is single degree of freedom system with book 1 constitutive model. And we consider the first passage probability. And the result is still similar to the previous one. And here we see the similar trend that the data is actually far away from the typical set region, but still the method gives reasonable good results. So, well, of course, there are many different directions for future research, but here, this one is the one I'm most interested in. Because recently, Dr. Marco Broccardo is here, and Professor Junho Song and I developed some Hamiltonian Monte Carlo-based subset simulation algorithm. And this Hamiltonian Monte Carlo is somehow the state-of-the-art MCMC method. And we combine this with the subset simulation, and we build some subset simulation algorithm. And so one future research direction is to integrate the hyper-spherical formulation with this subset simulation approach. So the summary is straightforward. We have the hyper-spherical formulation, and we have developed 2 different methods. The first one is importance sampling approach, and the second one is extrapolation approach. And these 2 are the papers about these 2 methods. Well, finally, this is ICASP 13 will be held at Seoul National University, and Professor Junho Song will be the chairman. So he is asking me to do some advertisement for this one. Oh, by the way, I think he should delete this because this research center no longer exists. Okay, so that's all. Thank you.